As the electrification of the world continues to expand, monitoring and understanding the power consumption and current draw levels of everything from our phones, our vehicles, and even the power grid itself is a priority. Hall effect sensors have become an unobtrusive way for engineers to measure the current in their systems. But what challenges exist in designing this technology in, and are there tools available to make it easier for engineers? Inductive current sensing has become one of the least obtrusive and best ways for electrical engineers to design current monitoring systems in their embedded applications. Whether we're looking at monitoring the current draw of our recharge circuit in an electric vehicle system, or the power consumption of a motor within one of our industrial robots, or even just monitoring the battery health of our phone, inductive sensing and Hall effect sensors are a great way to see the current that's being drawn from our batteries or being drawn by our loads in a very unobtrusive way that's very efficient for our system. At Future Electronics, we spent a lot of time with this technology, and we've recently developed our new Faraday Board, which is a great platform to demonstrate a number of different Hall effect sensors and current monitoring sensors that are available to electrical engineers, one of those sensors being from Melexis. Today I have the great privilege of talking with Paul Schmokel, Future Electronics' own advanced engineer responsible for analog and power, and also with Bruno Boury, product line manager of Melexis for their Hall effect sensor portfolio. Gentlemen, thank you so very much for joining me today. Really appreciate you being here with us on The Current.
Thank you.
Well, the pleasure is all mine, Todd. This is my first podcast.
So, when we talk about Hall effect sensors and what's going on with that, can you give me, maybe, Bruno, a little bit of an overview of what Melexis is doing with Hall effect sensors today? Kind of what current sensors are available from Melexis, what kind of range for voltage and power are available, and where the technology is going right now?
Sure. So, Hall effect is in Melexis DNA. So we've been making Hall effect sensors since the 80s. I was very young at that time, so I did not live it from day one. But as it has evolved, I think Hall effect technology has continued to gain on accuracy and gain market share with more and more addressable applications. When we look at the portfolio of current sensors at Melexis, we have two types. We have what we call the external primary sensors, where the current is flowing outside of the IC through a bus bar, a cable, or even a PCB trace for that matter. And those applications tend to be really more for higher power. We're booking a lot of business today in automotive inverters. Electrification is all over the place. Yeah. If you want to power a battery electric truck, you need 1,000 amp plus type of inverters. And we're able to monitor those kinds of currents. But those currents flow in a separate conductor. And then we have the so-called integrated primary portfolio. And this is actually the latest addition, which, by the way, found its way onto your Faraday board. And those integrated primary solutions, they are actually such that the current is flowing first through a PCB trace, but then it is going through a small SOIC package through the lead frame, in and out. And we're able to indeed inductively measure with Hall effect the amount of current that is flowing. And what makes that solution very neat is that it's a very tiny footprint. So, PCB board space tends to be expensive. People try to make things smaller, and we're able to integrate in a small package the current conductor itself, the signal conditioning, and the voltage isolation. And that makes it a very good value proposition.
Absolutely. And so, I think that adds the ease of design. The small footprint is critical in so many of the applications I mentioned. And then I also imagine there's some cost considerations and benefits to that as well, being able to integrate everything into one package and really just one device, which is definitely a great thing. What are some of the benefits of going with a Hall effect sensor as opposed to some of the more traditional? You mentioned that this kind of technology started back in the 80s when we were all very, very, very young. On this call, right? And so before that, I think we were using current sensor resistors and things like that. What are some of the benefits you really see customers taking advantage of with the Hall effect sensor technology that's available today?
Well, I think current sensor resistors are not going to go away. So they will still have their key application benefits, and we should keep that in mind. Everybody knows Ohm's law. It's the most linear one we know as an engineer, so that's a great thing to build on. But I think where Hall effect is able to position itself is particularly when you need isolation or when the current gets really, really big. And so the bigger the current gets, the more, let's say, intrusive a shunt resistor solution will be, because you get the self-heating from the shunt, and that's an RI squared law, which means it's quite thermally challenging to do it. And then whenever you need voltage isolation, by definition, a shunt solution is a contacting solution. You measure the two terminals of the resistor, which means that you need to take care of isolation downstream, be it with optocouplers or capacitive couplers or whatnot. So Hall effect is by definition contactless, and then for those integrated current sensor, and I forgot to actually answer your question before, we're targeting with our integrated current sensor typically applications up to 50 amps. Whenever the current get higher, we try to have other Hall effect offering, but then the current is flowing outside of the package. And that's again for thermal consideration. So what is the key benefit of Hall effect? It's mostly the fact that we also, we are intrusive with those integrated primary solutions because the current is forced to go through the package. But as opposed to a shunt solution where the size of the resistor defines the amount of signal you get, in our case, the amount of signal is not defined by the resistance of the lead frame. It's actually defined by how close and how performing our sensing elements are with respect to the current flowing in that current conductor, that lead frame. And that's actually the advantage, is that we are positioning ourselves in a way that where shunt resistors bring, I would say, thermal losses, and you want to intentionally put a series resistance in between to get a signal. With those Hall effect solutions, we are actually minimizing the resistance of the lead frame and the intrusive voltage drop that you get across it. So that's a particular benefit. And then when people say Hall effect in magnetics, historically, I mentioned Ohm's law before. It's extremely linear. When people talk about magnetics, you start thinking about ferromagnetic properties, which means saturation, linearity errors, 0 amp inaccuracy, what we call hysteresis or magnetic offset. And that's correct the moment you integrate ferromagnetic material, which is the case for the higher currents. However, for those integrated current sensors on the Faraday board, for example, we have stripped those components entirely of any ferromagnetic material, which means that those magnetic offset concerns, they no longer exist for that kind of product. So it's virtually offset free, and that makes it at least substantially more in the accuracy region of what you achieve with those current resistors. So that's one key benefit. And then, as I mentioned before, the fact that it integrates everything is definitely an important advantage as well. So
yeah, if I could add to
those
that,
are two key points where.
Yeah, if I could add to that, I would say the ease of integration, that is something you've got to look at the total cost of implementation. That's a big piece there, because let's say, for instance, looking at an EV charger, you're bringing an AC level 1 EV charger. You're going to bring that current in, you're going to use a relay to open and close that voltage, that AC voltage bringing through. You could use a current shunt amplifier, but now you have to deal with once again, you got to deal with the heat loss, but you're also dealing with the isolation piece. Secondly, you could maybe use, let's say, a current transformer, but there again, you're looking at something where you've got a donut, and you're bringing wires up, in, and back down through. So now you're talking a manufacturing application issue to deal with, as well as, once again, the outputs of that would have to be signal conditioned before you bring that into your micro. So here's something you seriously just bring it, the connector. You've got the connector, the power goes in, you run it right through the SO8 package and right back out, and then the output of that just goes right into the micro. It's got the signal conditioning, it's got the filtering, and all the buffering that you need for it.
No, that makes a lot of sense. And then, so, what about from terms of accuracy? As we get into more and more applications, we've talked about electric vehicles and being able to monitor the current in that realm. You can kind of see as things are going to, instead of using a gas pump or something like that, we're now having cars that are pulling up and plugging in, and the actual providers wanting to charge the user per amount of charge required for the vehicle to recharge that battery. So that gets into an aspect of you've got to be highly accurate so that you're charging the right amount. And certainly there are legal ramifications, everything else there. How accurate are Hall effect sensor methodologies for this compared to some of the more traditional methodologies we've had in the past?
Well, one of the key things that we always took pride in at Melexis is that we want to definitely play the accuracy card. I'm not here to claim that those sensors will reach class 0.x worth of accuracy that you have in metering and billing grade type of applications. Nonetheless, I think what we're targeting with these kinds of devices is that we have a 1% accuracy. And then what builds on top of that, you should probably count on the fact that over the full temperature range, and again, here we bring a bit of our automotive background at Melexis, is that those devices have definitely been designed to cope with minus 40 till 125 degrees plus capabilities. If you add in the thermal budget as well, you should probably add another percent. So I think by 2% all in, you will definitely be able to cut it. And then, of course, some applications allow for, let's say, a regular type of, I would say, recalibration or auto-zeroing or whatnot that can even contribute further to a more narrow error budget scope, let's say. But I would definitely work a 1%, and then on top of that comes some effect of thermal effect. So I would say with 2% all in, you're definitely in the right ballgame.
Okay, makes sense. And then, have you seen some unique applications and things that we haven't talked about for Hall effect sensors and things that our embedded engineers are looking at for these sensors that maybe are out of the norm a little bit?
I would say,
well, out of normal. Maybe Paul, you want to take this one?
The latest and the best one is EV charging right now. That is specifically an AC level 1, level 2 EV charging. Because what you're doing is you're bringing the AC signal, the house voltage or wherever the voltage source is coming from, right onto the car and using the vehicle's onboard charging system. Thereby, all you really need to do is you're looking at monitoring the current flowing through it. You want to have isolation. You're monitoring AC signals, and you're using a relay to switch in and out. The last piece is maybe using a little another sensor for, let's say, ground fault detection. But nonetheless, it's a very easy, non-obtrusive. Your electronics are almost entirely isolated from that AC signal chain going to the vehicle. So that's the number one, I would say. Bruno, what would you say the other ones would you run into?
Well, I think definitely you took the most evident example, which is actually gaining a lot of traction today. Next to that, I think we see it a lot here in Belgium, where I'm coming from. You get a lot of solar installations, right? I mean, residential solar systems, it's trying to pick up. Everybody wants to have a kind of decentralized power generation to make sure you can even disconnect yourself from the grid at some point. And in these solar inverters, you have maximum power point tracking, and on the DC side, there's also monitoring, which requires the necessary amount of isolation. And to have a quite elegant small chip solution with high isolation capabilities, that's definitely another application. You mentioned in the beginning, Todd, about factory automation. When I speak about electric drives, whenever you need to control an electric motor, there is phase current monitoring to monitor the torque and to have the control algorithms of the motor running well. Definitely, I mean, this is again a very good device that plays a role there and that gained a lot of traction. I think that's actually the one where we built the first successes in the beginning. Power supplies is another one where I think of uninterrupted power supplies. When you have an entire server farm running, or even just your household server that has a lot of data. I mean, if you have power outage, you definitely want to have an uninterrupted power supply where those conversions to a DC battery and back out to an AC signal. I mean, all these things need to be monitored. So there's a bright future for current sensing in general. And the applications get very crazy. I mean, lately we've seen another application together with Future that was coping with fitness. We never got the details of what happened exactly, but I mean, it was relatively big. So there are a lot of applications today that we don't even think about from the start, but where these kind of tiny components solving a lot of engineers' problems can have great sense. So
right. No doubt. I mean, I think the applications out there are myriad. It's more than just wanting to measure our system, and I think it used to be just in very sophisticated applications and things where we were trying to do maybe bench understanding of things. But now we want to understand our embedded systems in real time. We want our embedded systems to make decisions about their own health. in real time. And there's no doubt Hall effect sensors certainly help us with a lot of that. Where do you see the technology going over time as far as advancements? I mean, like you said, it kind of started in the 80s, and it's going to continue, obviously, to get better and better as time goes on. What, Bruno, do you see as the next steps in these current sensors?
That's actually a good question. So I would say unveiling a bit of what we want to do in the future. I think the journey that Hall effect, and particularly open loop Hall effect, because that's the technology we're talking about here. You also have closed loop technology that tends to be a bit more expensive, but also gains a bit on accuracy. I think what open loop Hall effect has done over the last 10, 15 years is really gain on accuracy and close the gap with a number of technologies. So I think that's one trend that definitely we will see continuing. I think as the world becomes also more digital, many of our sensors in the past were analog. The more we go digital, and that does not mean you cannot have an analog output, but if you do the DSP, the signal processing in the digital domain, I mean, you can squeeze the performance lemon to the fullest. So that's definitely one of the paths that Melexis is following. The packaging side, the sensors in the past, and when people think about Hall effect, they always think about an IC and then a ferromagnetic core where the sensor is placed in an air gap. The bulkier stuff. If you see now with the component we've been able to integrate on your board, on the Faraday board, you actually realize that you can measure up to 50 amp, almost RMS in a small 1 square centimeter footprint. So packaging is a key thing. I mean, people need to find solutions to integrate, and integration is the only innovation driver, I believe, for the future. So we'll definitely continue there. And one of the things we're of course exploring is we set the barrier right now for the integrated solutions up to 50 amp. I mean, definitely we want to push that barrier and go to 100 amp because power PCBs and power density is increasing. So we want to invest in that. So accuracy, we mentioned the packaging aspect. And then I think there are some, in the past, you develop a current sensor that was addressing all applications. I believe now the future is asking for more and more dedicated products per segment and per application. And then that means that battery and motor control, it's two different areas. Of course, with a high-speed sensor, you can also address a low-speed application, but some specific requirements may require products to be modified in a particular direction. So I would say extrapolation of the things from the past, focus on package, focus on integration and value add and integration of function. And that's another one worthwhile to mention. On the component that we've integrated, there is also on the SOIC 16 footprint, so the slightly bigger one of package, we have also a dedicated overcurrent detection output. And that's a safety function that, the moment a short happens, you need to protect your IGBTs and your power electronics. And having a dedicated 1-bit output that tells you, look, there's a problem, we need to disable the system. In the end, it's saving comparator on the board. But by integrating that comparator, we bring more value to our customers, and you need less footprint and less space on the PCB. And I think that's the key trend that we should continue to build on.
Agreed.
So obviously, some exciting things happening with the technology. And we've talked a lot about the future electronics Faraday board and what we've developed so that embedded engineers can take a look at these different Hall effect sensors from Melexis, can use it for prototyping, can use it for proof of concept in your designs to see if those sensors are going to be a good fit. And then also, we make the full files of our design available to embedded engineers such that you can use our schematic, our BOM, our layout, and take basically what we've done and incorporate it directly into your designs fairly easily. I know Lazina Rahman had done a nice demonstration of the Faraday board. Paul, would you mind walking us through that demonstration?
Yes, absolutely. Here you see the Faraday board. It consists of 4 channels. 2 channels utilize Melexis' isolated Hall effect current sensors, and 2 channels employ a traditional precision resistor and current sense amplifier combination. Channels 1 and 2, shown here on the left with terminal blocks, use the Melexis MLX 91220. The 91220 have options for current sensing up to 75 amps. In the case of the Faraday board, we're employing the 25 amp version. Current flowing through the 91220 is measured, processed, and an isolated 0 to 5 volt analog signal is output, which is proportional to an input current from negative 25 to positive 25 amps. This output can then in turn be sampled by any microcontroller's A to D input. Here we're utilizing the Infineon's PSOC 4. Channel 3 utilizes USB Type-C connectors for input and output connections. This channel employs a Faraday precision resistor and a diode's ink current sense amplifier. The channel is capable of measuring up to 5 amps and once again outputting a 0 to 5 volt signal for the Infineon PSOC 4 to measure. Finally, channel 4 is a fixed 5 volt source from the micro USB connection seen at the top left corner of the board. Incidentally, this is also the power source for the entire board. Using the USB Type A connector shown at the bottom center of the board, you can measure loads of up to 300 milliamps. Once again, this current is measured via a Faraday precision resistor and a diode's ink current sense amplifier. To operate channels 1 and 2, simply connect your power source and load to the terminal blocks and press the appropriate channel to view voltage, current, and power on the OLED display. It is worth noting that you can measure the efficiency of a power supply by connecting it as shown. Power into the device under test comes from channel 1 output, and power out of the device is then fed back into channel 2. This allows you to measure the power in, the power out, and calculate the efficiency. And lastly, you can also capture all the information via a terminal emulator program such as TerraTerm.
Yeah, great. I mean, I saw the video once. Now with the voiceover from Paul, it's even more clear how to use it. And I mean, definitely for companies like Melexis, it's good to be part of a bigger, I would say, ecosystem and environment where many more components are built together. And I think one of the key things that engineers are looking for today, it's solutions. I mean, you don't want to have the hassle and burden of acquiring a few components together. I think what Future has been able to do is to make a board that solves evaluation problems of customers and that they can try it out, go ahead, play, unboxed, and be ready to go in 30 seconds. I think that's exactly what we achieve here. And then if we can be part of that with Melexis, I mean, that's a great story. Bringing voltage isolation, integrated current sensing with voltage isolation up to 4.8 kilovolts should enable, I would say, a myriad of applications. And we look forward to see how this unfolds and how it's received on the market. So thanks a lot for being part of that.
Well, Bruno, thank you and Melexis for your support with this board. We're really excited about it. We think it brings a lot of value, and to your point, offers a solution to embedded engineers to expedite their designs and get them successful designing in Hall effect sensors from Melexis more quickly, which we think is always the goal of any of the support we're trying to provide into the market. So, Bruno, Paul, thank you guys so much for your time and your expertise. Really appreciate you talking with me today. Thanks all for watching the video and watching the current. We really appreciate your time, and we hope that this has brought a lot of value to you. If you have questions on Hall effect sensors, on Melexis, on Future Electronics Faraday Board, we would absolutely love to help you and talk with you about the solutions that we offer. Please reach out to us at Shaping the Future, one word, Shaping the Future at futureelectronics.com. We would love to help you in your designs. Thanks to all, and have a wonderful day.
Thank you.
Thank you for having me. Goodbye, everybody.